So here we have root node. So this is essentially looking at a GP tree, but looking at it from looking down on it, on top of the root node. So essentially, each branch within the tree is given an equal angle. As we move away from the root node, those angles become smaller and smaller. So on this long, thin spike actually represents quite a large number of different nodes. But you can see how, obviously how far we are from the root node. The advantage of this type of representation is we can project multiple trees onto the same coordinates. So we can actually stack up the whole population on top of each other. And here we're coloring the nodes within the trees according to their individual phenotype. So this is the phenotype of nodes rather than of the whole individual. So remember that, because we're going to come back to it in a moment. The paper itself covers a great number of different things about convergence. What we're looking at is a traditional symbolic regression, but we're going to run for up to 100,000 generations. What we'll do is look at evolution of convergence. We start by looking at the size and shape. So although the populations converge, we have to be careful what we mean by that, since everybody in the population is unique. The paper considers that, considers the convergence of fitness, considers the convergence of nodes within the trees. And the part I've highlighted there is it also looks at not just node contents, but also their runtime. So essentially, phenotypic convergence within the tree. One of the surprises was we're expecting that the trees would blow to this bloat would be entirely due to obvious introns, but it turns out that the fraction of introns within the trees is highly variable. In some cases, it's being almost none, and in some cases, the trees are almost entirely full of introns. The various other aspects that are covered by the paper, but I wanted to concentrate in particular on looking at the evolution of phenotypes. So if you remember the picture I showed you before of a tree, here we have a tree where the X and Y axis have grown enormously. So our tree is now 200 or 300 levels deep. So the distance from the origin is the depth of the tree. And again, as I said, we stacked our trees on top of each other. So the trees are projected in the XY plane, and then the vertical axis is the number of individuals in the population which have the same phenotype at this particular point in the tree, yeah. So, and the colors indicate the phenotype. So you can see here almost the whole of the population has identical values, although this is only effectively 1 pixel wide. There is still variation that between members of the population, which doesn't really show up because we're dominated by the most popular phenotype in the population. So just to let that animation run. So you can see over time we move away from the origin, and the population has a high degree of phenotypic convergence. Okay, so going back to the slides. So essentially, we've just seen an animation of that picture where the XY is the tree position, and then the vertical is the degree of convergence in the population. So as I said, the paper covers a lot of different aspects of convergence. Essentially, the population is converging because we have very strong tournament selection. As the trees evolve, they become not only bigger but also deeper, meaning the crossover points are further away from the root node. So there's a longer path. The disruption caused by crossover has to pass along, and therefore there's more chance that the crossover disruption will be lost before it propagates as far as the root node. If it doesn't reach the root node, then the child has exactly the same fitness as the parent, and that in turn also encourages strong convergence. We can look at this from an information theory point of view, which, as I said, leads to the long paths from the crossover point to root node leads to failed disruption propagation. This, following on from this, we might think about different ways of designing our crossover and mutation operators. We might also look at designing test sets so that the tests are more effective at finding the impact of crossover. We can also consider the function sets in terms of their information characteristics. For instance, protected division is particularly lossy operation, but so too are things like conditionals and booleans. So those have a high entropy loss, so they lead to much faster failed disruption propagation. Essentially, what we see is information loss giving rise to a smoother fitness landscape. So evolution tends to slow, but it nevertheless still continues. And